Hello, here's three more questions on electric fields and related matters. We're starting here with the usual define electric field strength. We've had this quite a few times. This is the force per unit positive charge. So easy definition to get us started. Part B, we got an evenly spaced grid with a positive charge Q at point A. We've got the magnitude of the field strength at point B is this, 8 times 10 to the 5 newtons per coulomb. Apart from the magnitudes of the electric field strength, state another difference between the electric fields at points B and C. Right, so yeah, electric field strength, this is the force per unit positive charge, because we're saying what would happen if we put a positive charge into the electric field. That's giving us the direction that the charge would move in. So if we got a positive charge here at point A, as we have done, it said we got a positive charge. So the direction of the force at B is going to be away from A, force at C is going to be away from A. So we've got a difference in direction at points B and C. Determine the magnitude of the electric field strength at point C. Well, electric field strength is our E equals F over Q. That's our force per unit charge. So we know with F that we've got the 1 over R squared relationship between the force and the distance from A. C is twice as far away from A as B. So we're going to be saying that, yeah, C is 2 times distance from A. Therefore, E at C will be 1/4 of E at B. So that's going to be 2 times 10 to the 5 equals 2.0 times 10 to the 5 newtons per coulomb. Right, so that's a nice warm up there. The next part, right, this looks more involved. The simplest atom is that of hydrogen with 1 proton, 1 electron. Right, there we go. They've given us the mean separation between the proton and the electron, 5 times 10 to the minus 11 meters. Calculate the magnitude of the electrical force acting on the electron. Right, so Coulomb's law. So we want Q times Q. So that's going to, well, they've got the same charge, haven't they? So 1.6 times 10 to the minus 19. We need to square that. Divide by 4 times pi times epsilon 0. So 8.85 times 10 to the minus 12. Multiplied by the square of the separation. So 5 times 10 to the minus 11 squared. All right, let's do a quick bit of simplifying before sticking all of that into the calculator. So 2.56 times 10 to the minus 38 divided by, well, we've got a 5 squared is 25, multiplied by the 4 gives 100. So 885 pi times 10 to the minus, how many have we got here? 22 and 12. So, yeah, 34. So off to the calculator we go. 9.2076 times 10 to the minus 8. So 9.2 times 10 to the minus 8 newtons to two significant figures. Right, the gravitational force Fg acting on the electron due to the proton is very small compared with the electrical force it experiences. Right, calculate the ratio between what we've just calculated here, which is Fe, and then Fg. Right, so we've got to go back to Newton now and get our Fg. So our Gmm over R squared. So universal gravitational constant, 6.67 times 10 to the minus 11. Then we need the mass of the electron, 9.11 times 10 to the minus 31, multiplied by the mass of a proton, which is 1.67 times 10 to the minus 27. Then we need to divide again by our 5 times 10 to the minus 11 squared. So it's just plugging in loads and loads of numbers and getting those This is take a while to type in. Let's just leave out all of the powers of 10, make it quicker, and then I can stick that in at the end. So 4.06 times 10 to the minus 47. Wowzers. Okay, so yeah, that is small, but we'd expect it to be small. And then we need the ratio between the two. So Fe divided by Fg is equal, what was our Fe again? So 9.2076 divided by that. So 2.3, and we'd have 39 left, wouldn't we? So 10 to the 39. Right, that's good. A simplified model of the hydrogen atom suggests that the de Broglie wavelength of the electron is 4 times the mean separation between the proton and the electron. Right, okay. So estimate the momentum of the electron and the kinetic energy of the electron. Right, so our de Broglie wavelength, that's the Planck constant divided by the momentum. So we've got then that the momentum is going to be equal to our Planck constant, 6.63 times 10 to the minus 34, divided by what they've told us the de Broglie wavelength is, which is 4 times this. So that's going to be 2 times 10 to the minus 10, isn't it? 2 times 10 to the minus 10. So we're going to have 3.315 times 10 to the that should have been, I said 10 and wrote 11, times 10 to the minus 24. So 3.3 times 10 to the minus 34. Don't forget your units, kilograms, meters per second, because we're looking at momentum. That's the two significant figures. And then we need the kinetic energy of the electron, right? So kinetic energy is equal to half of the square of the momentum divided by the mass. So, you know, this is for the electron, so we're using our 9.11 times 10 to the minus 31 for the mass. So, you know, we've already got momentum there. That's why I'm using this rather than half mv squared, because I've already got this number sitting in the calculator. Just makes it a little bit easier. So 6.0314 6.0314 times 10 to the minus 18 is our kinetic energy. So 6.0 times 10 to the minus 18 joules. Two significant figures. Right, okay, that wasn't too bad. Quite a lot of calculator work again, so I'm never really a fan of, because it's the easiest thing to mess up on these is just putting a wrong number into the calculator. Or doing what I nearly did here of saying one thing, 10 to the minus 10, and writing down another one. So yeah, it's fiddly rather than anything else. Anyway, onwards. Figure 1.1 shows a close-up of the two electrodes of a spark plug. Electrodes may be considered as two parallel plates. Electric field strength between the electrodes is almost uniform. Define electric field strength, right, yet again, force per unit positive charge. Separation between the electrodes is 1.3 millimeters. Electric spark is produced when the electric field strength is that. Estimate the potential difference between the electrodes when the spark is produced. Right, well, obviously from the, well, units, if nothing else. We're doing our, you know, E equals V over D on this. So we just need to multiply our electric field strength by the separation, and that'll give us the voltage. But you can, as I say, you can see that from the units. We're just multiplying these two numbers together. So we're going to have that our potential difference. So 1.3s is 3.9. And then we got a 10 to the 6 times to a 10 to the minus 3. So 10 to the 3 volts. Right, so that's that bit done. The electric spark lasts for that amount of time with that amount of average current. Calculate the charge transferred between the electrodes. Right, they're taking us back to GCSE days then. Q equals IT. So we're just multiplying these two numbers together. Well, we got 4 times 2.7 will be 10.8. So 1.08. We've got an extra 10 onto that 10 to the minus 11, makes it 10 to the minus 10. So 1.1 times 10 to the minus 10 coulombs to two significant figures. calculate the number of electrons transferred between the electrodes. So that's going to be our 1.08 times 10 to the minus 10 divided by 1.6 times 10 to the minus 19. So oh, it's going to have to go to the calculator, isn't it? So we got 6.75 times 10 to the 8, which is 6.8 times 10 to the 8 electrons. Right, that's fine. Estimate the total energy transferred by the electrons in that last part of the question. Right, okay. Well, our energy is our volts times our charge. You know, voltage, potential difference is joules per coulomb. So that's the number of joules we're getting for every coulomb. So if we multiply our coulombs and our voltage, then happy days. So our voltage was 3,900, and then our 1.08 times 10 to the minus 10 is our charge. So 4.2 times 10 to the minus 7 joules. Right, that was a really easy question, that one. First one was a bit more interesting. Right, I'll do one more. Figure 1.1 shows a circuit, two parallel plates, high voltage power supply, separation between the plates is in the picture, PD is in the picture, there's a vacuum, and we're accelerating electrons across the gap. Calculate the force acting on an electron when it's between the plates. Right, so our usual thing here with parallel plates, electric field strength is V over D, which is also F over Q. So our force between the plates is going to be V times Q over D, which is 2400 multiplied by 1.6 times 10 to the minus 19 for an electron, divided by 9.4 times 10 to the minus 3 for the separation. So off we go, 4.085 times 10 to the minus 14, which is 4.1 times 10 to the minus 14 newtons to two significant figures. What's the gain in kinetic energy of an electron when it travels from A to B? Right, well, that's just going to be, well, the kinetic energy is going to be equal to 2400 electron volts. I mean, you could just multiply the 2400 by the charge on the electron, and then that'll actually have it in joules, but that's fine, isn't it? What is the speed of the electron when it reaches plate B, assuming that it starts from rest at plate A? Okay, so how quickly is this going to be going? So we've got our half mv squared is equal to this. So V is going to be equal to the square root of 2 times 2400 times 1.6 times 10 to the minus 19. So that's our kinetic energy multiplied by 2 divided by the mass. 9.11 times 10 to the minus 31. So tap all of that in. Again, oh, this one's going to take even longer. But yeah, you can see we didn't actually save very much time by putting electron volts on the last one, because we still had to work it out in joules anyway. Right, finally got there. 2.9 times 10 to the 7 meters per second. Right, final part, part B. Separation between the plates is doubled, but the PD across the plates is kept the same. How would this affect the answer to A part 2? So the kinetic energy. Would the kinetic energy change if we've doubled the distance between the plates? Well, it wouldn't, because well, the energy, we know that the energy is equal to the voltage multiplied by the charge. Well, the charge isn't changing and the voltage isn't changing. This is not a function of D, of separation. So it doesn't make any difference. You know, whatever you do, it doesn't matter how long it takes to move a charge through a potential difference, you're still going to get the same energy change once you've completed that transition. So yeah, okay, so the second two questions were much easier than the first one, but again, it's all just calculator work stuff, but you get so many of these questions in exams. not particularly interesting. But you know, you have to practice them nonetheless.